Hello everyone. Welcome to our third lecture. Today we embark on an essential journey into the core of operating systems with our topic processor management in operating systems. Today's lecture will be part 1 and next lecture will be part 2 of it. This lecture will explore how operating systems effectively manage one of the most critical components of a computer, the processor. Now, our focus will revolve around understanding the roles and responsibilities of processor management in ensuring efficient system performance. We'll delve into concepts such as the role of the CPU in operating systems, the significance of scheduling processes, and the algorithms that guide this scheduling. Now, by the end of this lecture, you'll gain a solid foundation in how processors are managed within an OS environment and understand the fundamental mechanisms that drive multitasking efficiency and system optimization. Okay, now let's start by understanding the essence of processor management in operating system. So the processor or CPU is the brain of the computer. It's responsible for executing instructions that power all the process and applications we use. Without the CPU, a computer simply cannot function. So processor management within an operating system plays a critical role. It ensures that the CPU's resources are efficiently utilized by scheduling tasks, managing different process states, and optimizing resource use. Now, essentially, it's about keeping the processor busy and working efficiently to handle multiple tasks while also ensuring fair allocation of resources to all processes. Now we'll also explore how processor management achieves these goals and why it is a fundamental aspect of operating systems. So, as I already said, the CPU often referred to as the brain of the system and its critical role within the operating system. The CPU is at the center of all computing operations. It interprets and executes instructions from both applications and the operating system. Now, every task that requires computation or decision making goes through the CPU, making it the most vital component of the system. Then in the context of operating systems, the CPU is responsible for multitasking. Now this means efficiently switching between multiple processes, ensuring that each one gets the CPU time it needs to execute, whether it's running a complex algorithm or responding to user input, or managing system tasks. The CPU operates seamlessly under the guidance of the operating system. So this efficient coordination between the CPU and the operating system allows for smooth performance even when multiple applications or tasks are running simultaneously. So as we move forward, we'll also discuss how the OS handles CPU scheduling to achieve this efficiency. Okay. Now that we have understood the role of the CPU, let's discuss an essential aspect of processor management, which is CPU scheduling. Now, CPU scheduling is the process that determines which process in the system will execute next on the CPU. With multiple processes waiting to use the CPU, the operating system must decide the order in which they will access this critical resource. So the goals of CPU scheduling are threefold. Like first of all, it is to ensure fair allocation of the process among all processes, and to maximize CPU utilization, ensuring the process is working efficiently and it isn't sitting idle unnecessary, and to minimize waiting time for processes and improving overall system performance and responsiveness. Now, efficient CPU scheduling is vital in achieving multitasking and system optimization. Now, here we'll take a closer look at the algorithms that help manage CPU tasks effectively. Now, operating systems use a variety of scheduling algorithms to determine which process gets access to the CPU at any given time. Now, these algorithms are designed to achieve fairness, efficiency, and performance optimization. Some of the most common CPU scheduling algorithms include first come, first serve, which is where processes are executed in the order they arrive in the ready queue. Then also this method is simple but can lead to longer waiting times for processes arriving later. Then shortest job first. So the process with the shortest execution time is given priority in this algorithm. And this also minimizes waiting time but can result in starvation for longer processes if shorter jobs keep arriving. We'll also learn about starvation later. So third is round robin. So each process is assigned a fixed time slice and the CPU cycles through them in order. This ensures fairness and is particularly effective in time sharing systems. And so these algorithms are tailored to specific needs and workloads. Okay, now let's begin with the simplest and one of the most intuitive CPU scheduling algorithms. First come, first serve. Now, in this process, like in this algorithm, processes are executed in the order they arrive in the ready queue. There is no prioritization. It's a straightforward first come, first serve approach. While simple and easy to implement, this algorithm has some limitations. As we'll see, here is an example. Now assume there we have three processes. First is P1, P2 and P3. Now if P1 requires 4 milliseconds of execution and P2 requires 3 milliseconds and P3 requires 2 milliseconds. Now the execution order in first come first serve will be P1, P2, P3, right? So based on their arrival order. Now the corresponding Gantt chart here, you'll see P1 start at 0 millisecond and then it finishes at 4 millisecond. Then P2 then start and finishes by 7 millisecond, and then finally P3 completes at 9 millisecond. Now let's evaluate the performance. The average waiting time can be calculated as waiting time for P1, P2, P3, so and which can be divided by the total process. Now while FCFS is simple, it can lead to inefficiencies such as the convoy effect. Now if you so where shorter processes have to wait for longer process to complete. Now if you see here, we are substituting the values 0, 4, 7, we are adding these values and then substituting by 3 because the total processes are 3. Now you will see 3.67 millisecond is the average waiting time. So if you look at here, the P3 have the shortest process time, but it has to wait because P1 and P2 has to be finished before P3 can start. So that's why it has a very long waiting time, but the process time is smaller than the waiting time. So in that way we can have more waste we can waste more time in the CPU. So that's just this highlights the need for more advanced algorithm, which we'll explore next here. So we'll now explore shortest job first. This algorithm prioritizes processes based on their burst time, meaning the process with the shortest execution time is executed first. So the main advantage of shortest job first is that it minimizes the average waiting time for processes, making it one of the most efficient scheduling methods. However, it comes with a significant drawback, which is starvation. Like processes with longer burst times may experience indefinite delays if shorter jobs keep arriving. So let's see an example here. We have P1 with a burst time of 6 milliseconds, then P2 with 2, and P3 is 1. And in shortest job first, the execution order will be P3 first, because the P3 have the shortest burst time, which is 1 millisecond. So it will be P3, P2, then P1. Now as P3 has the shortest burst time, followed by P2 and P1. Now if you look at the Gantt chart here, P3 starts at 0 millisecond and finishes at 1. Then P2 runs and finishes by 3. Then finally P1 runs from 3 to 9. And here the average waiting time is 1.33 millisecond, which is more reliable than the previous one. So SJF significantly reduces the average waiting time compared to FCFS. However, it's important to consider the potential downsides, such as the possibility of process starvation. So we'll discuss these limitations further, because if you look at here, if you add another process P4, which has a shortest process time, then P3 have to wait again. Okay, now let's see round robin scheduling algorithm. Here it is widely used in time sharing systems to ensure fairness and responsiveness. In round robin, each process gets a fixed time slice called a time quantum in a cycling order. If a process isn't completed within its time slice, it's moved to the back of the ready queue to wait for its next time. So this method ensures that no process is left waiting for too long, making it highly suitable for interactive systems. Now if you look at the example, the time quantum is 2 milliseconds. We have three processes. P1 have a burst time of 4, then P2 3, and P3 is 2. Now the execution follows a cyclic order. Now P1 gets the CPU for 2 milliseconds, but since its burst time is 4 milliseconds, it goes back to the queue after its time quantum. Then P2 runs for 2 milliseconds, leaving 1 millisecond of its burst time remaining, and P3 completes its execution in 2 milliseconds. Now the remaining times of P1 and P2 are processed in subsequent cycles. So if you look at this Gantt chart, first we'll starting from 0, then 2, 4, 6, then 8, then 9. Now finally let's calculate the average waiting time. So the waiting time is 5 milliseconds, because P1 and P2 has to wait again to finish its process. So um, well, it is effective in ensuring fairness, but the performance heavily depend on the size of the time quantum. And if the quantum is too small, the system spends more time context switching. If too large, it behaves like first come first serve. So the next algorithm we'll explore is priority scheduling, which introduces the concept of assigning priorities to processes. In this method, processes are executed based on their priority. The process with the highest priority is executed first, regardless of its arrival time or burst duration. So, the priorities can be either pre assigned by the system or dynamically adjusted based on factors like process type or resource requirement. So if you look at the example, we have three processes P1, P2 and P3. Now P1 has priority 3 and P2 has priority 1 and then P3 has priority 2. Now then it will go by this order with the highest priority. So the execution order will be P2, P3, P1 because P2 is priority 1. So the well, it ensures that critical processes are executed first. However, this approach can lead to starvation, where lower priority processes might never get executed if higher priority processes keep arriving. So, to address starvation, modern systems often use techniques like aging, where the priority of a process increasing the longer it waits in the queue. Next, we'll look at a more structured and hierarchical approach to scheduling, which is multi-level queue scheduling. In this algorithm, processes are divided into multiple queues, each representing a specific category or priority level. For instance, system processes, interactive tasks, and batch processes may each have their own queue. So, the operating system assigns processes to these queues based on their characteristics, such as priority, type, or resource requirements. So, each queue operates independently, and processes within a queue are scheduled based on a specific algorithm, like first come, first serve, or round robin. So, for inter queue scheduling, a predefined priority hierarchy determines which queue gets access to the CPU first. So, for example, we have interactive tasks like user commands might be placed in a high priority queue to ensure responsiveness, and batch processes such as background computations might be placed in a lower priority queue to avoid interrupting user interactions. So, this method is beneficial in environments where processes have distinct priorities or characteristics. However, it may suffer from starvation for lower priority queues if higher priority tasks dominate the CPU. Okay, so now let's discuss an essential process in multitasking operating systems, which is context switching. So, context switching is the process of switching the CPU from one process to another. It allows multiple processes to share the CPU effectively, and creating the illusion of simultaneous execution in a multitasking environment. So, the operating system saves the current process state into its process control block, which is PCB. This includes registers, program counters, and other crucial data needed to resume the process later. And then it loads the next process state from its PCB, allowing the CPU to resume execution of the new process. So these are the steps involved in context switching. Now, for example, imagine switching between a text editor and a web browser. When you switch tasks, the operating system saves the text editor state so it can be resumed later. Then it loads the state of the web browser to continue its execution seamlessly. Now, key points to note here is context switching is essential for achieving multitasking and CPU efficiency. And but it comes with overheads since saving and loading process states take time and resources. Excessive context switching can lead to performance degradation, often referred to as context switching overhead. So here is a diagram which illustrates the process of context switching with a simple diagram that breaks it down step by step. Here we have a process A. Now the system begins with process A currently running on the CPU. At some point this process must pause, either because it's waiting for an input output operation or another process has a higher priority. Its time, or it could be its time slice has ended in a multitasking system. It could be anything. So before moving to the next process, the state of process A is saved to its PCB, process control block. This includes its registers, program counter, and any other information necessary to resume it later. Then once process A's state is saved, the CPU is now free to load the state of another process. Then the state of process B is loaded from its PCB, which includes all the data needed for the CPU to continue or begin executing process B. Now finally, the CPU switches to executing process B, continuing where it left off or starting its task. So this diagram highlights the back and forth nature of multitasking in an operating system. While context switching enables efficient CPU utilization, it comes with overhead cost as the CPU spends time saving and loading states rather than performing actual computation. So this visual simplifies the concept, showing the cyclic nature of saving and loading states, which is at the heart of multitasking systems. Okay, now let's focus on an integral component of process management, which is process control block. The PCB is a critical data structure in the operating system. It acts as a repository of information about a process, enabling the operating system to manage and control the process effectively throughout its life cycle. So whenever the operating system switches between processes, it relies on the PCB to save and retrieve the necessary data for each process. Now here are some key components of a PCB. First of all, we have to have a process ID. So this is a unique identifier assigned to each process. It allows the operating system to distinguish between different processes. Otherwise, how it will know that which process is which. Then second, we have a process state. Now this tracks the current state of the process. A process can be in one of the several states, such as new, ready, running, waiting, or terminated. And this ensures the OS knows what stage the process is in. Okay, so third is program counter. The program counter stores the address of the next instruction the CPU needs to execute for this process. This is crucial for resuming the process after a context switch. Then last we have CPU registers. These registers hold the current working data for the process. During a context switch, the values in these registers are saved to the PCB and restored later when the process resumes. So the PCB acts like a snapshot of a process, holding everything the OS needs to manage it effectively or efficiently. Without the PCB, processes could not be paused, resumed, or switched seamlessly. Okay, next is memory management information. This includes details about the memory allocated to the process, such as base and limit registers or page tables. It ensures the process has access to the memory it needs while preventing unauthorized access to other processes' memory. Next is scheduling information. This stores the process priority, the scheduling queue it belongs to, and other data required by the CPU scheduling algorithms. And it also enables the OS to efficiently schedule and manage multiple processes. Next is I/O status information. Now it tracks information about the I/O devices allocated to the process and open file descriptors. I/O means input output. So this ensures smooth handling of input output operations. And then the last one is accounting information, which includes metrics like CPU time consumed, memory usage, and other resource statistics. This is especially useful for performance monitoring, billing in shared environments, or debugging. Now here is an example. We'll see role of PCB in context switching. Like when the operating system switches from one process to another, the current process state is saved into its PCB, ensuring that it can resume seamlessly later. And the next process PCB is loaded, allowing the OS to continue or start its execution. So the PCB acts as the brain of process management, holding all the data needed for the OS to manage a process life cycle. Okay, now here we'll see the illustration of the life cycle. So the life cycle of a process through a state transition diagram, which helps us understand how processes move between different states during their execution. Now the diagram highlights the following process states. We have new. So a process begins in the new state when it is created. At this stage, the operating system has acknowledged the process but hasn't yet placed it in the ready queue. Second, we have ready. So once the process is ready to execute but is waiting for the CPU, it enters the ready state. All required resources except the CPU have been allocated at this stage. Then running. When the process is assigned the CPU, it transitions to the running state. Here the process executes its instructions. Then waiting. If the process needs to wait for an input-output operation or an external event, it transitions to the waiting state. Once the event is complete, the process moves back to the ready state. Then fifth is completed or terminated. When the process completes its execution, it transitions to the terminated state. The operating system releases all resources allocated to the process. Now here in this diagram, it represents the life cycle of a process. We have so from new to ready, when a process is admitted by the operating system. So the process is going from new to ready. Then it is going from ready to running when the CPU process is scheduled on the CPU. Then it going to running, from running to waiting when the process is waiting for an event, and then from running to terminated when the process completes its execution. And also it goes waiting to ready when the event the process was waiting for is completed. So this is how this the life cycle works. This state model ensures that the CPU is utilized efficiently and resources are managed dynamically based on process requirements. Okay, now here we have a visual representation of multi-level queue scheduling, which we discussed earlier. So here the process are grouped into distinct queues based on their characteristics such as priority or type. Each queue is managed independently and may have its own scheduling algorithm. For example, one queue might be FCFS, while another use round robin. So high priority queues, the processes in the high priority queue are executed first, ensuring that critical tasks like system processes or interactive user tasks are handled promptly. And low priority queues are executed only after higher priority tasks have completed or are waiting. So this operating system the operating system assigns processes to different queues based on their attributes such as priority levels, resource requirements, or process types, as we discussed earlier. And then each queue is scheduled independently, but the queues themselves are organized in a hierarchical structure. So this visualization helps us see how higher priority queues are given preferences, while lower priority queues may experience delays. To mitigate starvation in lower priority queues, techniques like aging can be employed, gradually increasing a process priority if the wait is too long. Okay, now this slide provides a comparative overview of primitive and non-primitive scheduling, two fundamental approaches in process management. Now, in primitive scheduling, a process can be interrupted if a higher priority tasks arrive. This ensures responsiveness and better handling of critical tasks. In non-primitive scheduling, a process runs to completion or until it voluntarily moves to a waiting state. It doesn't get interrupted by higher priority tasks. Then, primitive scheduling offers better responsiveness for high priority tasks, making it ideal for real-time and interactive systems, where non-primitive scheduling may lead to higher waiting times, especially for critical or short tasks stuck behind long processes. Then primitive scheduling requires context switching, making it more complex to implement. The OS must save and restore process states frequently. So then non-primitive scheduling, which is simpler and easier to implement because it avoids the overhead of context switching. Then starvation. In primitive scheduling, starvation can occur if high priority processes continuously preempt lower priority ones. This can delay or even indefinitely postpone the execution of low priority tasks, where non-primitive scheduling eliminates starvation since tasks are executed in their entirety without interruptions. So primitive scheduling algorithms like round robin and shortest remaining time first. These are the examples of this approach. And non-primitive scheduling algorithms are first come first served and shortest job first. These are the examples. So we'll see some real examples here. So first one, the primitive scheduling scenario is like we are using the round robin algorithm with a time quantum of 2 milliseconds. Then we have three processes, each has 6 millisecond, 4 millisecond and 2 milliseconds burst time. Then P1 executes for 2 milliseconds, remaining 4 milliseconds, and then P2 executes for 2 milliseconds, remaining 2 milliseconds. P3 executes for 2 milliseconds, which completes the task, and then again it resumes P1 for another 2 milliseconds, and P2 resumes for another 2 milliseconds. So this is the Gantt chart here, and this example shows how round robin ensures fair CPU time distribution by cycling through processes, improving responsiveness. And here it switches before the context. So there are interruptions, and then it saves the P2 or P3 task in the PCB, and then resume it again for to complete the total task. Where on non-primitive scheduling, if we use first come first serve, it doesn't interrupt by anything, and it completes its own task without any interruption. Alright, so let's discuss now a significant issue that arises in process scheduling, which is starvation. Now, what is starvation? Starvation occurs when low priority processes are perpetually delayed because high priority processes continuously take precedence. This leads to some processes never getting the CPU time or resources they need to execute. So, starvation is most commonly associated with priority based scheduling algorithms, where processes with high priority dominate system resources. So, what is the cause of starvation? So, first of all, continuous arrival of high priority processes are the first cause. Like if new priority tasks keep entering the queue, low priority processes are never scheduled for execution. For example, in a priority based scheduling algorithm or system, a background process with low priority might remain in the queue indefinitely because critical tasks keep arriving. Second is inefficient scheduling algorithms. Now, some scheduling algorithms like priority scheduling without additional mechanisms can inherently lead to starvation. So, this happens because there's no safeguard to ensure lower priority processes eventually get CPU time. Now, third is limited resources. When resources such as memory or CPU cycles are scarce, high priority tasks tend to monopolize these resources. This leaves nothing for lower priority processes, causing starvation. Now, starvation is a serious issue in scheduling systems as it affects the fairness and efficiency of process execution. To mitigate starvation, techniques such as aging are used. So, we'll also explore and learn about aging later. Now, let's see an example where we have a priority scheduling system We have priority queue with the following processes: P1, P2, P3. Um, so P1 has a high priority and it requires 10 milliseconds to process. Then P2 have high priority requiring 5 milliseconds, and P3 has low priority requiring 3 milliseconds. Now the execution order will be P1 and then P2, and then new high priority processes keep arriving, and then P3 will wait indefinitely. So P3 can begin execution only when there is no new high priority processes arrive in the queue. So as a result, P3 is continuously delayed, potentially waiting indefinitely as higher priority processes keep preempting it. This is a classic example of starvation. Okay, now that we have identified the problem of starvation in scheduling systems, let's explore the strategies used to prevent it. These solutions ensure that all processes, regardless of priority, eventually get their fair share of CPU time. Now, first one is aging. Now, aging involves gradually increasing the priority of waiting processes over time. Now, this ensures that processes waiting for an extended period eventually get a chance to execute. For example, a background task waiting for 10 minutes might get its priority boosted from low to medium, ensuring it gets CPU time for execution. This is a common technique used in priority based scheduling to balance responsiveness and fairness. Second is fair scheduling algorithms. Now, algorithms like round robin are designed to ensure equal CPU time for all processes, regardless of priority. So, by assigning these time slices to processes in a cycling order, round robin reduces the risk of starvation as no process can monopolize the CPU indefinitely. Um, Third is dynamic priority adjustment. Well, uh, so dynamically adjust the priorities of processes based on wait time or system conditions is the dynamic priority adjustment. For instance, a process that has been waiting too long or is critical for system functionality might have its priority elevated temporarily to ensure timely execution. And these techniques ensure that scheduling systems are fair and minimize the risk of indefinite delays for low priority processes. The choice of solution often depends on the system's requirement, balancing between responsiveness and efficiency. Okay, so here we'll see a practical example of FCFS scheduling, where we have a printer in an office which processes jobs in the order they are received. So for example, we have three jobs, J1, 2 and 3, and it execute in this order, J1, J2, J3, because it first come first serve. So here we have this Gantt chart and matrix where we have average waiting time 3.33 millisecond and average turnaround time is 5.67 millisecond. Then next we have an example of SJF scheduling, where we have a restaurant kitchen which prioritizes preparing simpler dishes to serve faster. So we have three jobs, but J3 requires 1 milliseconds to complete. So and the first one is J. So it starts from J3. The execution order is J3, J2, and J1. So and after all of these and after all three is done, the average waiting time is 2 milliseconds. and the average turnaround time is 6.33 milliseconds. Next, we have a example of round robin, where we have a CPU in a computer which alternates between multiple user programs, ensuring non-starves. So it ensures that there is no starvation. So for example, the time quantum is 2 milliseconds. Then we have three jobs, and the execution order will be J1, J2, J3, and then again J1, J3, and J1. So here the average waiting time is 5.33 millisecond, and the average turnaround time is 9.67 millisecond. Okay, now let's discuss an important topic in process management, um, which is real-time systems and scheduling. Now, what are real-time systems? Basically, real-time systems are computing systems designed to respond to inputs or events within a strict time constraint. So the timing is critical here, and the system's functionality is tied not only to what tasks are performed, but also to when they are performed. So some applications of real-time systems are like real-time systems are used in scenarios where even slight delays can lead to system failure or severe consequences. For example, in healthcare, if there is a life support machines or heart monitors which require real-time responses to ensure patient safety. If there is any even a slight delay, it could risk patient's life. So next is aviation. Um, flight control systems depend on real-time decision making to maintain safety and efficiency. So these are just example. We'll also see some more example in coming slides. So here there are two types of real-time systems: hard real-time and soft real-time system. So in hard real-time, um, the hard real-time systems are systems where tasks must be completed within strict deadlines. Failure to meet these deadlines can result in catastrophic consequences or system failure. So the key characteristics here is the deadlines are non-negotiable. So this is very strict. The deadlines are very strict, and missing a deadline leads to critical failure of the system. For example, air traffic control systems or pacemakers, industrial robotics, these are the example. On soft real-time systems, um, deadlines are important but not critical. Missing a deadline degrades performance, but the system continues to function without catastrophic failure. So here the key characteristics are, we can say deadlines are flexible and performance depends on meeting them. Missing deadlines results in lower quality of service but not failure. Like video streaming, online gaming, these are examples for low soft real-time systems. Okay, now here let's take a closer look at the key characteristics that define real-time systems and make them suitable for time-critical applications. First of all, determinism. Real-time systems emphasize predictable execution of tasks. This means that the system's behavior, how and when tasks are executed, must be well defined and consistent. For example, in a hard real-time system, every task must complete within its predefined time frame, ensuring the system operates without failures or delays. Second is priority-based scheduling. Real-time systems utilize priority-based scheduling where high priority tasks are executed before lower priority ones. This ensures that critical tasks such as responding to a safety hazard in an industrial plant are handled first. So, effective prioritization is essential to meet deadlines and manage time sensitive operations. Third is resource allocation. It is crucial for real time systems because they ensure the efficient use of CPU memory, and IO resources so that tasks are not delayed due to resource unavailability. For instance, in a pacemaker, precise allocation of CPU time and memory ensures timely detection and correction of heart rhythm. And poor resource allocation can compromise system performance, especially in high demand environments. Okay, now we'll see some real time algorithms. Um, so, to ensure tasks in real time, systems are executed within their time constraints. Specific scheduling algorithms are used. Now, let's see. First one is rate monotonic scheduling, RMS. RMS is a static priority scheduling algorithm where tasks are assigned priorities based on their periods. So, tasks with shorter periods, like higher frequency, are assigned higher priority. For example, task A has period 5 millisecond priority high, and period task B has period 10 millisecond and priority low. In this case, task A will always preempt task B due to its shorter period. Then second, we have earliest deadline first. So EDF is a dynamic priority scheduling algorithm, meaning a task prioritizes these are recalculated during execution um, based on their deadlines. So tasks with the closest deadlines are executed first. For example, we can say task A has deadline 4 millisecond and task B has deadline for 8 millisecond. So the execution order will be task A, then task B, because task A has the earlier deadline. Then third is fixed priority preemptive scheduling. FPPS assigns fixed priorities to tasks, and higher priority tasks preempt lower priority tasks when necessary. This algorithm is simple and efficient for systems where task priorities don't change dynamically. It is often combined with aging techniques to prevent starvation. Okay, now we'll see an example of real time scheduling in aviation. Um, so here the scenario is like in aviation systems, multiple tasks need to be managed simultaneously. Here we have two key tasks. First is collision detection and then weather updates. So for collision detection, which is a hard real-time task, this task is critical for ensuring safety. Missing a deadline could lead to catastrophic consequences. For example, the system must detect and respond to potential collisions within milliseconds. Where on weather updates, which is a soft real time task, um, while important for flight planning, but missing a deadline for weather updates does not have immediate severe consequences. And these updates can tolerate minor delays and can be rescheduled when the system has idle resources. So to for scheduling approach, We can say collision detection is assigned the highest priority to ensure it is executed immediately whenever needed, and weather updates are scheduled only when the system is idle, meaning they are executed after higher priority tasks have been completed or when resources are available. Okay, so for real life examples, as I we already discussed earlier, um, so on healthcare, like monitoring the patient's vital or in ICU or heart disease. So on automotive systems, systems like anti-lock braking system rely on real-time operations to ensure safety. um, so the ABS detects wheel speeds in real time and adjusts braking pressure to prevent skidding. um, on multimedia, ensuring it just ensures smooth video playback without buffering, which is an example of a soft real-time system. Okay, now to better understand process scheduling, we need to differentiate between CPU bound processes and IO bound processes. These two categories have distinct characteristics and requirements that influence how they are managed by the operating system. On CPU bound processes, it spend most of their time performing computations. They rely on they rely heavily on the processor to execute complex calculations. Um, so they require extensive CPU cycles to complete tasks. Their performance is limited by the speed of the processor, meaning that faster processors can significantly reduce execution times for these tasks. For example, scientific simulations, mathematical computations, and data analysis tasks. Where in IO bound process, it spend most of their time waiting for input output operations to complete, such as reading or writing data to a disk or network. They are limited by the speed of IO devices rather than the CPU, and these processes frequently wait for data transfers, making them dependent on faster IO devices for improved performance. So these are computation heavy tasks that spend most of their time executing on the CPU. So we just discussed the same thing earlier in our previous slide. So this is just a table for their features. Um, so for example, as I already said, to ensure these processes require longer CPU burst, and these processes benefit from algorithms that reduce context switching to maximize CPU efficiency. And first come first serve and shortest job first, these two are example for CPU bound process. And on IO bound process, these processes benefit from algorithms that prioritize quick execution and responsiveness. So the example is round robin algorithm, which assigns equal time slices to each process. So to consider the scheduling here, as I said, it requires longer CPU burst, and IO bound process requires shorter CPU burst but frequent scheduling. So basically this is all about the comparison between CPU bound and IO bound processes. And that's the end of our today's slide, and that's the end of part 1 of processor management. On next lecture we'll have part 2 of this processor management, in in operating system. Um, so thank you all.